This is IAT 355 Lecture 12, Multiple Views. So today we're going to be talking a little bit about what happens when you end up with too much data. Of course, that's been an issue that we've been facing as projects get big, as the visualization data set that you're looking at gets big. And what we're going to do is talk a little bit about how to deal with too much data. So the first segment is going to be about, first off, what does too much mean, and what are some ways of dealing with it that don't introduce any new abstractions or new technologies. And then we're going to be talking about some ways that do introduce new technologies in the facets section. Okay, so the primary problem is that you often end up with data sets that are very, very large. Perhaps for your project, that's not such a big problem, but, and that's merely because I imagine you went along with my suggestion that you don't make your data too big, because among other things, that you'll have to run your program and it'll take its time and so on and so forth. And often what happens is that if you end up using a data set in its full enormity, you end up with obviously lots of data, and you end up with the problem of what's called overplotting sometimes. So here's a scatter plot that is just a scatter plot of some random data. It's a value of x versus value of y, and what we're doing here is plotting a single opaque circle for every single scatter plotted point. And what's happening is that there's so many data points that you end up with this kind of blue trilobular blob. It looks like there's the outlines of three circles here, very, very roughly speaking. And that's not too terribly informative, because once you add the fourth or fifth dot to, say this region here, you've kind of run out of color bandwidth at that point, and you can't really do much. And as a visualization, because there's too much data and each scatter plotted point is plotted on top of all the other ones, you're ending up reaching a point of diminishing marginal utility. So there are a number of ways to deal with this without stepping outside of the paradigm of a single scatter plot. So one of the ways to deal with that is to simply plot smaller points. Recognize that, if you've got your data set up, recognize that your data set is very large, and therefore each individual scatter plotted point is, by contrast, by dint of it being in a large body, relatively unimportant, and so just reduce the size of objects. And that's the first thing here. And so here are some smaller scatter plotted points. Another thing to do is to remove the fill color. Those are filled circles. You could just draw outlines, and so that at least leaves some white space around the, within the point if, the thing you're drawing is of sufficient size. And so you can see more overplotted points in a particular region. Another thing is to change the shape from some kind of container, size circle or square or triangle or something, to a non-container, say an X or something. So the location of the point is still depicted directly at the crossing point at the X, but there's simply less extra ink being plotted, or less pixels being filled, and you get to see the locations of the points. Another thing, which makes sense from a computer graphics perspective, and particularly if you're dealing in a space that is somewhat quantized, is to jitter the data. Just add, for each individual data plotted point, just add a small perturbation in X and Y, an equal amount, a random amount, and that can sometimes serve to make the points a little bit more comprehensive. But that's, you don't see that used too often, but that kind of so-called jittered sampling is something that is just out of the standard computer graphics, 3D computer graphics bag of tricks, is to sample randomly, or at least pseudo-randomly, in a way that it gives you the opportunity to accumulate points and have them be visually comprehensible. The sort of more obvious point that you're likely thinking of, and perhaps you read ahead as I was talking, is to make the objects transparent or translucent. That is to say, instead of plotting opaque points, in this case some kind of opaque blue, make the points that you're plotting have an alpha value or a transparency value of 50% or 25%. So 25% opaque is what I mean by that. And every time you draw, you add the contribution of the new drawn point onto the whatever the pixel values that are currently at that location where you're plotting. And what that serves to do is to de-emphasize each individual point somewhat. It makes all the points still visible, although the uncommon ones are a little faint. And that's what's going on here in this diagram. In this middle plot here is that we're plotting semi-transparent points. And so you can see, compared to this one, somewhat more detail as to the overall density. And so what adding transparency ends up accumulating density visually or graphically by accumulating and accumulating in the alpha channel every single time you plot. This density measures thing is the suggestion, and this is often used as one of the well-known techniques in volume rendering, is to, instead of plotting a single circle, which is uniformly transparent across, have instead a circular region in which it's, somewhat opaque in the center, and it falls off smoothly, typically with a Gaussian function or a normal distribution, to completely transparent at its periphery. That's what the kernel density estimation, KDE, thing is about. And that serves, once again, to show you where the points actually are, and at the same time reduce the amount of overplotted stuff. Last on this list is on the bottom right, is to do something a little different, and that is to create a display in which there's an intervening accumulation buffer, if you will. And its purpose there is, instead of doing graphical techniques to accumulate in the alpha channel and of course accumulate color, instead what you do is you quantize the space possibly at the same density as you would intend to draw it, say 1,000 by 1,000 pixels for the sake of argument. And instead of accumulating accumulating pixels, what you do is you accumulate the values of the data set, the scalar values of the data set, the single quantities of the data set. And each of the locations where you're doing this accumulation, instead of being 8 bits for alpha, is a floating point number. And then what you do after you've rendered, as it were, all that stuff into that floating point rectangular array, you then do a second pass. And then you compute a contour where the highest density area is in the center, and then do contour rendering at that point. So that's transforming a scatter plot, in which the x and y values of the location of the data points is random, so to speak, for each data set. That mixes sort of InfoVis techniques with scientific viz techniques, where you transform the discrete region into a continuous field, or you treat it as continuous. And so that's what's going on here. So think of this as being very similar to a terrain that's sea level around here, and there are two mountaintops. And what the mountaintops are intended to depict are the density of points at that location. There are some tools out there that do that. So one of the tools that does that, of this accumulation of data points, is something called FlowJo. It's a funny name, but its job is to visualize data coming from flow cytometry machines. And what flow cytometry machines are is things that you inject into it, essentially a biological sample that, say, has a bunch of cells, and the machinery of the flow cytometry flows a cell one by one past a bunch of lasers that measure the size, the shape, the density, and possibly, if there are fluorescent tags attached to the cells. You end up with a high-dimensional database, and of course you end up with millions of data points because there's millions of cells in the sample. And what you want to do is show the density, the quantity of cells with a particular size and a particular shape and a particular density per cell. And because you have millions of data points, if you didn't do anything special, you'd end up with a plot that looks like this one up here. So instead, what FlowJo does is this accumulation game that you see down here. The plots look a little different from this, but that's the basic idea. Okay, as the last comment on the previous slide said, there's only so much you can do with computer graphics techniques, and I just wanted to mention them to, sort of check them off, as it were. one of the challenges, of course, is it's not just that there's a lot of data, there's also likely a lot of dimensions. And it's the fact that there's a high dimensionality that is one of the challenges in doing visualization. And one of the primary concerns that you would have is it's hard to map patterns and relations across sets or across elements of the set, particularly if you have multiple tables. And what this ends up delivering to you as the user or the analyst of visualization is visual fragmentation, having to kind of keep in your mind the relationship amongst the segments, as it were, of the data set that you've got. And you end up having to decode many different visual forms, and all that work of decoding creates problems for you as the analyst in terms of memory limitations, your own memory limitations, and cognitive limitations. Up here on the upper right is one avenue that I have explored in my research work, is to use 3D to do 3D scatter plotting. And so this thing, certainly it's a reasonably well done 3D scatter plot, but in order for this to work well, you have to apply a bunch of computer graphics techniques. So here we're plotting the cars data set. This is gas mileage along this dimension. This is 0 to 60, the acceleration time, and this is power measured in kilowatts. And here are the 2D scatter plots. This one on the floor is mileage versus 0 to 60. This one here is power versus mileage, and this here is 0 to 60 versus power. Okay, so the vertical dimension here is common on these back planes. This direction going this way is common here and here, and the dimension that runs from here to here is common here and in this back plane. And of course, those 3 dimensions are mentioned here. So the same point is plotted 4 times. 3 times in 2D on the back surfaces and once in 3D on the front surface. In order for this to work, as I think I mentioned before, really this thing has to be capable of being moved readily, either with a mouse or with 3D trackers, say, using VR gear. If you don't have that, these 3D displays are hard to understand. But with that, it helps, but it certainly takes some practice to be able to understand it. So 3D, sometimes, however, 3D plotting and graphics techniques kind of run out of gas, and they just don't seem to make sense for the data set. So here is a plot of the city of Vancouver. This is a geospatial plot, and what we're plotting here is a bunch of real estate data, including categorical data about the relative proportion of buildings of particular kinds. So you have one family dwelling is red, 2 family is orange, light orange is multiple. Comprehensive development is green, so there's a big comprehensive development domain here in the downtown area. Commercial is yellow, etc., etc. So those are all each, in some sense, dimensions for buildings in the city. And what is intended to be gotten across here is the kind of distribution of what kind of buildings are where. And it's multiple dimensions, a number of counts per location. And so you really have to stare at this thing to get a good sense of what's going on. And probably our right thing to do is to really enable interaction to help you with understanding what's going on in that. So that previous example is plot is an example of using icons or essentially freestanding, more complex micro visualizations per location in order to get across the underlying complexity of the data set. And in icon plots, each icon represents a single multivariate case. So each of the regions in the Vancouver city is a location of a multivariate case. And the emergent visual appearance is some kind of unique visual identity. And you could see in the Vancouver plot, if I go back one, that clearly there are different visual identities here versus here versus here. Right? Different composition of housing, commercial, industrial, depending on where you are in the city. And yes, there is some industry in the city that's located right here, or one of the places it's located is here. It used to be that a lot of industry was located around the Falls Creek area, but that stopped about 30 or 40 years ago. And industry, in that sense, moved elsewhere in the Lower Mainland region. Going back to the glyphs again, each icon represents a single multivariate case, and each location with this complex glyph has this unique visual identity. And it's useful for small data sets that have up to 10 variables that you're intending to pack into, say, that pie chart that we're showing there, or these other representations, either circular or sequential over there on the right. So the limitations of this technique is that it's suitable for modest numbers of dimensions, a handful or two, and small data sets. The other thing is that if you were to do this as a technique, you kind of want to make the decision once as to what the order of things are, and stick with that order for every plot. If you start reordering things, then that will really serve to confuse the viewer. And so plotting of glyphs can be done in two ways. One is circular, shown here in the upper right and also indicated with pie charts. In pie charts, the angle of the segment indicates the quantity. In this circular plot that I'm indicating up here, it's the distance from the center. So let's talk briefly about each glyph. So what you can do is to create essentially a glyph form and then map information to this form. And what that, of course, is asking the user to do, the analyst, is to, sort of really learn how that form works. And if you're going to use it constantly, you have an established practice at some organization, or you're going to create a new practice, you'll want to design that and once and change it very infrequently, and really mark that it's different on this plot versus that one. You can also consider stacked bars, as shown here on the right, as examples of glyphs. They're kind of glyph-like, and that is they're intended to be read as the little collection. So there's one here, 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 here. So there's 4 glyphs in this plot on the right. Here's another variation on that. This is scatter plotting along some dimension, and we're showing a little bar chart at each scatter plotted point to indicate that there's 4 more variables. Yeah, 4 more variables at each of those scatter plotted points. And you could, once you accept this and are decide as the analyst to expend the time to understand things visually, you can start to tease apart what's being depicted here. This is something where it's in your best interests to, as a visualization designer, or you as the user selecting what the visualization is, to have a clear idea of what's primary and map that to the standard dimensions of X and Y and color and so on. And then what's secondary, which is what's going to go on in each one of these little glyphs. So to get a little bit more organized about this, there are a couple of techniques. We haven't talked about them much. I think we've shown scatter plots in parallel coordinates in passing, is to transform the concept of what is a plotted data item, instead of being, sort of a unified, localized set of visual information, is to transform the concept of what is to be plotted into something a little different. And in both of these cases, the parallel coordinates on the left and radar plots, or sometimes called star plots, on the right, what is a data point is, in this instance, a single polygonal line. So there's a data point in here that has a location here, this where the value of that data point in this dimension is 0. That's the origin, or very low. This is the year. This is the acceleration, weight, horsepower, displacement, cylinders, miles per gallon. And so what is a data case? A data point case is a single polyline that moves through the data values of each of the dimensions. So there's a scatter plotted point, a single point will be this, then this, drawing the line segment to here, to here, to here, to here, to here, and say to there. And what you do is, for every single one of the points in the scene, you add a polyline, where each polyline goes through each of the dimensions that are arranged horizontally. Radar plots are a radial version of parallel coordinates. Instead of laying out the coordinates in parallel along a line from left to right, what you do is you have a common origin being the center, and each of the dimensions is laid out radially from that center, and a single polyline, say, let's take the cyan one, joins the data values along each dimension as you move around clockwise for this. So these things are suitable for modest numbers of data, particularly the radar plots on the right. If there's a small amount of data, it's probably workable. And some of what you're intending to do is to get across the visual shape of the thing in addition to being able to read off the points. So it's not so great for doing things like retrieving value, mainly because you have to do kind of this extended amount of visual search. But parallel coordinates in particular are pretty good for adding dimensions horizontally. The other thing you can do with parallel coordinates and with radar plots is you can, when you're interacting with it, is you can rearrange where the dimensions are located horizontally. So here's another plotting of cars, in this case, individual cars being plotted here, and you can see how the shapes are a little bit different. And so these are older cars. So here's the El Seville, the Cadillac, the Eldorado. You can see that the horsepower is high and the miles per gallon is low, whereas compared that to the AMC Spirit, which is a smaller car, low acceleration, decent miles per gallon, one hopes. So one of the things that you would probably wish to do is, if you're doing parallel coordinates, is to get an indication of which dimensions are most alike. And as I said, probably the best thing to do is to, if you're doing or using parallel coordinates, is to be able to rearrange the dimensions. And I will show an example of that right now. And this is from, once again, the Mike Bostock's site. This is done by Jason Davis. So once again, here's the cars data set, and what you can do with this thing is you can, you have to go up to the title, economy, displacement, cylinders. You can rearrange the data set. And we see that there's a lot of crossing here. And now cylinders and displacement, you can see a very, strong correlation from number of cylinders in the engine and the correlation between that and the total displacement, which is the total volume of each cylinder when the piston is at, kind of the bottom of its travel in the cylinder. And similarly, you can likely do some rearranging in order to be able to get a good sense of this. So you can see the relationship between cylinders and power and displacement are all closely related to each other. Not surprisingly, it's a fundamental concept of engine design. And that is also related to miles per gallon. There's an inverse relationship. Higher power typically ends up resulting in lower fuel economy. And this is data from a number of years ago when engines were a little bit simpler. So that's gives you an example of how parallel coordinates can be used. Just a brief sketch, particularly when there's interaction, you can get some value out of this kind of plotting method. Parallel coordinates are not infinitely extensible. There are a number of graphics techniques that have the similar kind of problem. Namely, if you're drawing, standard polygonal lines for this thing, you end up with a lot of overdraw with this, but sometimes the overdraw is serving some useful purpose, but there becomes an upper limit, and there have been some investigations in using computer graphics techniques to be able to deal with overdraw in this technique. So at some point, however, you just end up with too many dimensions, and so this is another thing that has a relationship with parallel coordinates, a similar kind of technique. And, you can see that essentially the technique has resulted in this kind of complexity. This is a variation on the technique. Okay, so that wraps it up for multiple views, kind of giving a justification for what happens when you have too much data. So we'll stop it there.